morning, everybody. My name is Andrew Thompson. I received my PhD in neuroscience from UCLA fairly recently, and what I studied was the neurobiology of impulsive behavior in protracted withdrawal. So this has to do with primarily drugs of abuse. So let's start with some information about substance use disorder and sort of the global toll that it takes. As of 2014, unintentional poisoning by drugs and alcohol is the leading cause of accidental death in the United States. It exceeds the death toll of firearms and motor vehicle accidents, and that's not even counting motor vehicle accidents in which alcohol is a factor. This is strictly unintentional overdose by drugs. Additionally, in addition to the human costs of drug use, the economic costs of illicit drug use exceed $193 billion every year. And that includes costs related to crime, healthcare, and lost productivity. If you include licit drugs such as alcohol and cigarettes, then that figure jumps to $700 billion of a cost to the United States economy every year. And what makes this so difficult is that substance use is what we refer to as a chronic relapsing condition, meaning that even after a patient has been treated for their substance use disorder and been abstinent for a very long period of time, they still often relapse and begin again with the substance use disorder. And so this here is a chart showing the percent of a population of methamphetamine users in Los Angeles who were remaining abstinent a certain number of months after treatment. And as you can see, within 1 month of leaving treatment, approximately 40% of methamphetamine users had relapsed back to using the drug. Within a year, approximately 60% of methamphetamine users who had received treatment for this drug had relapsed. And there are a number of factors that contribute to relapse, and we'll discuss some of them. But one thing that I want to point out is that even after 6 years of abstinence, some people are still relapsing. So drug use is a chronic relapsing condition, and patients can relapse even after an incredibly long period of time. So what are some of these factors that drive relapse? The first two are fairly obvious. Drugs feel good. People like using drugs. This is what we call positive reinforcement. When you take a drug, it feels good and it makes you want to repeat that behavior. Negative reinforcement is related, and it is the fact that when you stop using the drug, it feels bad, and so you want to take more of the drug in order to get rid of the bad feelings. That's negative reinforcement. And these two are some of the principal drivers of relapse, especially early on after treatment. Additionally, we often talk about the fact that cues and cravings can cause relapse. Compulsivity or habits is this idea that as you're walking down the street and you walk past your favorite bar that you used to go to when you were drinking regularly, you just habitually go in and get a drink. So that can drive relapse. But in my mind, one of the most important things that drives relapse is impulsivity. And so that's what I'm going to be spending most of my time today talking about. What do we mean by impulsive relapse? Relapse that occurs swiftly and in the absence of conscious awareness of craving can be defined as impulsive. So this graph here shows the average amount of time for people who relapsed after a period of abstinence, the amount of time that passed between them deciding that they were going to use the drug again and actually taking the drug. And what we see is that for 40% of people who were surveyed, it took less than an hour for them from the time that they decided to use the drug to the time that they actually consumed the drug. A quarter of people reported times of less than 1 minute. So it's very clear that impulse control or poor impulse control can lead to problematic drug use and relapse. In fact, Bill W. of Alcoholics Anonymous described this phenomenon by saying, quote, "I saw I could not have so much as one drink. Shortly afterward, I came home drunk. Someone had pushed a drink my way and I had taken it." So this refers to an unthinking relapse. Why do we call it impulsive? Impulsivity is a very complex scientific construct which refers to the tendency to act without thinking or the tendency to prioritize short-term gains over long-term goals. And this tendency can lead to impulsive behaviors. So impulsive behaviors might be you're unable to wait your turn when you're expected to, or you're unable to resist a drink when it's placed in front of you. So it's clear to see how these impulsive behaviors can affect drug use. Impulsivity itself, though, is made up of a number of underlying factors. So these factors can include behavioral inhibition, or your inability to stop an ongoing behavior, can include insensitivity to consequences, or the idea that you don't care about what's the negative consequences that are going to happen to you, you just want the positive outcome, or lapses of attention. If you can't maintain attention on a long-term goal, then you're going to go for a short-term thing. All of these can be assessed with standard laboratory tests. So the first laboratory test of impulsivity occurred in 1978, and it was the Stanford marshmallow test. And what happened in this experiment was that the experimenter put down a marshmallow on the table in front of a child and told the child, you can eat that marshmallow now, or if you wait, I'll come back in a little while and give you 2 marshmallows as long as you haven't eaten that one. Of course, the experimenters were lying to the children, and they had no intention of coming back to give the children 2 marshmallows, but they waited and timed how long it took for the child to give up, stop waiting, and eat the marshmallow. 10 years later, they did a follow-up, and they found that the children who were able to wait longer periods of time were more academically and socially competent. They were better able to cope with stress. They had higher SAT scores, and they were more verbally fluent than their peers who gave up after a short period of time. So impulsivity is clearly a factor that predicts long-term success. We need to kind of operationally define impulsivity if we're going to have a scientific discussion about it. So I propose this definition. Impulsivity is an inability to evaluate and subsequently respond flexibly in search of a specific goal or outcome under changing environmental conditions. Now that's fairly complex, and we need to unpack that a little bit, so I'm going to unpack it with a couple examples. One, it could be an inability to use available information to reflect on the consequences of your actions. It could also be an inability to suppress an ongoing motor response. Or it could be an inability to forego an immediate small reward in favor of a delayed larger reward. So I'm going to really focus on this third definition, and this is something that we call delay discounting. So I'll ask the audience, would you, if I were to offer you $100 now or $110 in 60 days, which would you rather have? Who would take the $100 now? A couple of us. Who would take the 110 in 60 days? All right. So why wouldn't we all just take the $110 when it is objectively better at this point? The reason is that the value is discounted. So I'm going to just explain this graph here a little bit. The distance between these 2 bars is the delay to the receipt of the reward. The height of the bar represents the actual value of the reward. So here we've got our $100 bar. Here we've got our $110 bar. It is actually objectively higher in value, but it's delayed. And so what we see when we choose the later reward, the earlier reward, is that the value of the later reward has been discounted as a function of us having to wait for it. It has been discounted as a function of the delay. And its discounted value actually falls below the actual value of the reward. Now, everyone discounts at slightly different rates. So some of us would be okay waiting the 60 days. Some of us would prefer not to. Generally, it is considered that shallower discounters are less impulsive and steeper discounters are more impulsive. So if I wanted to assess whether or not, or assess how steeply someone discounts, I can modify this question. I can say, would you rather have $100 now or $110 in 2 days? At this point, most of us will be willing to wait the additional 2 days for the extra $10. I could also ask, would you rather have $100 now or $110 in 8 days? Now at this point, we might be more or less indifferent between the two. So the value of the larger later reward is about the same as the value of the smaller sooner reward. So once I've found this indifference point for an individual, I can do some complicated math, and I promise this is the only math in the entire presentation. And I can calculate what's called the discounting constant. And so for a person who's roughly indifferent between $100 now or $110 in 8 days, their discounting constant would be 0.0125. Turns out this is approximately the average for most people. By contrast, someone who is dependent on methamphetamine has a discounting constant of 0.045. That's a lot steeper. These people are going to be a lot more impulsive. So to put this kind of back into the context of money and time, the average person with this discounting rate of 0.0125 would be willing to wait approximately 20 days to get $25 over an immediate $20. By contrast, the average methamphetamine dependent person would only be willing to wait 5 days for that same benefit. So I kind of alluded to this before, but that's methamphetamine. It turns out steep discounting of delayed rewards has been reported in a variety of drug dependencies, including heroin, nicotine, alcohol, methamphetamine, as I just discussed, and cocaine use, as well as individuals with unspecified drug use histories. Now, one thing that we should definitely be aware of is the fact that maybe people who are more impulsive are just more likely to use drugs. Maybe it's not something about the drugs, but just these people are more impulsive. They value short-term rewards and short-term highs. Maybe they're just more likely to use the drug in the first place. Turns out that's true, but additionally there is evidence, and I'll get to this a little bit later, that drugs of abuse can induce impulsive choice behavior in the absence of pre-existing differences. And I'll get to that in a moment. So this brings us to the three major questions that I want to cover today. First, what is the neurobiological basis of impulsive behavior? Second, what is the relationship between impulsive behavior and substance use disorder? And third, how can we protect patients from impulsive behavior, which may include relapse, during protracted withdrawal? So let's delve into this first question. The neurobiology of impulsivity became a hot topic with the case of Phineas Gage. Phineas Gage was a railroad worker who most of you have probably heard of, and he was alive in the early 1800s, and part of his job was to take gunpowder and tamp it down into very small holes using a pole, and then that would later be set ablaze and explode to make big holes in the ground. Something went wrong one day, though, and there was a spark that came off of his pole, and it ignited the gunpowder underneath it, and it shot the pole like a rocket through his head, straight from his chin, and you can see the trajectory here, below his eye, up out of his head. And this damaged part of his brain, but he survived. And because he survived, we got the first really in detail account of what damage to this particular area of the brain does. So to understand kind of what it does, let's go to the original case notes. His doctor, Dr. John Martin Harlow, wrote that, quote, he is fitful, irreverent, indulging at times in the grossest profanity, which was not previously his custom, manifesting but little deference for his fellows, impatient of restraint or advice when it conflicts with his desires, at times pertinaciously obstinate yet capricious and vacillating, devising many plans of future operations which are no sooner arranged than they are abandoned in turn for others appearing more feasible. The first thing I would like us to note about this is the difference between case notes in 1868 and case notes now. I imagine most of us don't have case notes that look like this, but essentially what this meant to Dr. Harlow was that the equilibrium or balance between his intellectual faculties and animal propensities seems to have been destroyed. Now this language is very unique, and it's very actually characteristic for its time, because at the time it was thought that the higher nervous arrangements, meaning certain parts of the brain that were more well developed, evolved out of the lower, keep down those lower, just as a government evolved out of a nation, controls as well as directs that nation. This is a quote by Dr. John Hewlings Jackson in 1884, 20 years after the case of Phineas Gage. This notion of the brain, parts of the brain evolving to inhibit other parts of the brain, was codified in Paul MacLean's publication, The Triune Brain in Conflict, which was written in 1977. And Paul MacLean's idea was that the human brain is actually made up of three brains. First, there's what he called the reptilian brain, or the lizard brain. And this is responsible for all of the functions of keeping you alive, keeping you seeking rewards. It is a mindless reward-seeking portion of the brain that's only interested in acquiring food, water, and sex. Then the paleo-mammalian cortex, or what later became known as the limbic system, Paul MacLean thought was involved with emotion and emotional awareness, but importantly, it fought with the lizard brain. And then finally, the neo-mammalian cortex, the pinnacle of evolution in his mind. It was involved in suppressing animal desires and what we call executive function, and its role was to keep down the lower parts of the brain. Now, this model is very attractive. First of all, it makes humans the pinnacle of evolution, and we like that. However, and it survived. I mean, people still talk about the lizard brain as the part of the brain that's just mindlessly searching for rewards that needs to be inhibited by the more evolved neocortex. But when you get right down to it, this model is ridiculous. It is true, and it has been found that animals that don't possess a neocortex are perfectly able to exhibit cognitive flexibility and self-control over reward-seeking impulses. This has been demonstrated in lizards, birds, fish, honeybees, spiders. Some of these animals don't even have what Paul MacLean would have called a lizard brain. So clearly, cognitive flexibility does not depend on the existence of a mammalian neocortex. So this is kind of the old model of the neurobiology of impulsivity based on Phineas Gage, in that the prefrontal cortex, especially a region called the orbitofrontal cortex, here labeled as OFC, is involved in inhibiting behavior. This is kind of the old model, and what we've come to learn is that there's a lot underneath that. So the OFC may be involved in this, and the prefrontal cortex may be involved in this, but probably indirectly. Probably by signaling expected outcome values to other brain regions, which then make the decision whether or not to do something about it. So I'm going to focus specifically on one part of this diagram, which is this part here, the VTA, or ventral tegmental area projections to the ventral and dorsal striatum. So let's talk about the striatum real quick. The striatum is a part of the basal ganglia. The basal ganglia are a set of interconnected subcortical nuclei that form part of the brain's reward system. The basal ganglia are located deep underneath the cortex towards the center of the brain, incidentally in what Paul MacLean would have called the limbic system. And what they do is they're involved in motor control, and they act as a filter on motor commands that are coming down from the cortex, permitting action in the presence of reward predictive cues. I'll get to how that works in a moment. So what are the basal ganglia? Well, here, this ribbon of gray matter all around here is the cortex. And we're looking at a sort of a half of a brain and sliced like this. So we're looking at a front view of the brain. So this is all cortex, and these are sort of the deep brain nuclei. This section here is the striatum. It includes the caudate nucleus and the putamen. And that makes up the input region to the basal ganglia. So information, when the motor cortex wants to enact a motor command, it essentially goes through this and enters the striatum. Then it gets processed in complicated ways that I'll talk about in a moment. And the output comes from this other part of the brain called the globus pallidus. And the globus pallidus sends that information to the thalamus, and then the thalamus ultimately sends the go signal if permission is received from the basal ganglia. what makes the difference between the go signal and the stop signal is dopamine. So dopamine is a neurotransmitter, and dopaminergic cells, which are located in the ventral tegmental area, increase their firing rate in response to unexpected rewards and in response to cues that predict rewards, and they decrease their firing rate in response to omission of an expected reward. So this is one of the first demonstrations of that. It's from Dr. Wolfram Schultz's paper. And what he did is he trained a monkey, and he put a monkey into a setup that measured the activity of the dopaminergic cells, and he simply let the monkey sit there, and then every so often he would give a spritz of orange juice. And monkeys like orange juice. And so when the monkey wasn't expecting this, and it got the spritz of orange juice, here marked with this black line with the letter R under it, the dopamine cells, each dot here is the firing of a dopamine cell, and this line across the top is sort of their average across all the trials. The dopamine cells started spiking faster and releasing more dopamine. However, when he did something new where he played a stimulus, he played a tone, and then 1 second later he gave the reward. And he trained the monkeys so that they knew to expect this reward whenever the tone happened. What happened was that the dopamine signal shifted from the reward to the tone. So the dopamine neurons are no longer responding at all to the reward. They're actually just responding to the cue that predicts the reward. When he was kind of devious and played the tone but then didn't give the reward, the tone still elicited a dopamine response. However, there was a reduction in dopamine firing rate when the reward was supposed to be delivered but wasn't. So this is how dopamine works, basically. When you get a cue that there's something that you might want, or a good reward like the smell of coffee beans, then your dopamine will increase, and in a way that I'll talk about in a moment, that will allow you to go through whatever actions are necessary to acquire the reward. And if there's something off, if you take your sip of coffee and the milk has gone sour, then you will get a reduction in dopamine, and that will prevent future occurrences of that. So let's get a little bit into the nitty-gritty of how this actually works. Within the striatum, which again is that input region from the cortex to the basal ganglia, the cells are called medium spiny neurons because they are medium-sized and spiny and neurons. And they're divided into two populations. The first population expresses the excitatory receptor D1, which increases the cell's firing rate in the presence of dopamine. The other population expresses the inhibitory dopamine receptor D2, and these cells decrease their firing rate in the presence of dopamine. So what that looks like here is we have our D1 pathway, and they project to different areas. So we have our D1 pathway, which is called the direct pathway, and our D2 pathway, which is called the indirect pathway. The direct pathway is a go pathway. The indirect pathway is a no-go pathway. So essentially, these two are always kind of balanced at rest, with the indirect pathway being a little bit stronger, and that's what allows all of you to be sitting here right now not really moving, is that the indirect pathway is preventing any movement on commands coming down from the cortex, versus the direct pathway, which would allow movement. When movement is desired, the dopaminergic centers release dopamine, and that shifts the balance from the indirect pathway towards the direct pathway, from the no-go pathway to the go pathway. So in the presence of cues that predict reward, the balance will be shifted towards the go pathway, allowing you to act on any actions that will get you that reward. Conversely, when you want to withhold responding, dopamine will decrease, further strengthening the indirect pathway and preventing you from moving or doing whatever you need to do. So you can see how these neurons here are really able to control the output, the behavioral output of the brain, and can exercise inhibitory control over actions by reducing their firing rate. So these cells actually do receive input from the orbital frontal cortex or the prefrontal cortex. And so maybe the prefrontal cortex is playing a role in response inhibition and inhibitory control by predicting the value of actions and signaling that information to the ventral tegmental area so that the ventral tegmental area, or these dopaminergic cells, can tell the striatum whether to go or no go. So importantly, all of this valuation circuitry can be perfectly intact and working fine, but behavior can still be impulsive if somehow the striatum misses this inhibitory signal. How could that possibly happen? Well, the no-go pathway, as I've just described, is the center for inhibition in this model. So if that becomes insensitive to changes in dopamine concentration, then inhibitory control deficits can occur. One important point about the D1 and D2 receptors is that they differ in their affinities for dopamine, their baseline occupancy, and their sensitivity to changes in dopamine. So the D1, what's shown here is a trace of dopamine concentration during a spike and during a dip. And here is the occupancy of the receptors, D1 in red, D2 in blue, the occupancy of these receptors in response to the increase and the decrease. So you can see that when dopamine concentration goes up, D2 doesn't really notice. And what this tells us is that at baseline, the D2 receptors are pretty much saturated. Every D2 receptor, or almost every, it turns out to be about 75% of the D2 receptors are occupied at baseline. And they don't really increase much during, that occupancy doesn't increase much during these transient increases in dopamine concentration. So let's reduce this down to a easily understandable model. If you have 100 D2 receptors and you have 100 dopamine molecules, and you want to decrease the probability that you'll do an action by decreasing the amount of dopamine, then your D2 receptors will take note and they will stop the action. But if you only have 50 D2 receptors and you have 100 dopamine molecules, then a small decrease in dopamine might not change the occupancy of the D2 receptors. And so what's happening is you're missing this inhibitory signal. And in fact, low D2 expression does correlate with high rates of delay discounting and self-reported impulsivity in healthy human subjects. So D2, and specifically D2 in the striatum, seems to be a causal link between behavioral control and impulsivity. So just to summarize that real quick, the dopaminergic cells that project to the striatum are able to exert inhibitory control over behavior by reducing their firing rate. And low D2 expression in the striatum can cause the striatum to miss this inhibitory signal, leading to a failure to appropriately inhibit an action. Okay, so moving to our second question, we've kind of addressed a model for what might be the neurobiological basis for impulsive behavior overall. What does this have to do with drugs of abuse? What is the relationship between impulsive behavior and substance use disorder? Well, right away one thing becomes clear, which is that drugs of abuse cause increases in dopamine in the basal ganglia. So what's shown here is traces of dopamine concentration in the basal ganglia and in the striatum after administration of amphetamine, cocaine, morphine, ethanol or alcohol, and nicotine. And what we can see is that it increases the dopamine, all of these drugs increase the dopamine concentration. Now if you remember, that's going to activate the direct pathway and inhibit the indirect pathway. So there's one immediate causal link, is that all of these drugs of abuse are very closely tied to the dopamine system. Additionally, it is known that striatal D2 expression is reduced in methamphetamine users relative to controls. And so this is healthy controls doing an imaging scan and methamphetamine-dependent users, and we can see that they have fewer D2 receptors overall. Additionally, in human methamphetamine users, low D2 expression is correlated with greater impulsivity. So there's a link here between impulsiveness and D2 and methamphetamine. Additionally, we know by a variety of measures, including the Barrett Impulsiveness Scale, which is a self-report scale, that amphetamine users are more impulsive, self-report greater impulsivity than healthy controls, and actually that this difference can last up to a year after the person has stopped using the drug. We know that they have decreased motor inhibition, decreased ability to inhibit an ongoing motor response relative to nicotine smokers and non-smoker controls. And we know that they are more impulsive in terms of delayed discounting than healthy controls. Once again, this is all correlational data. It's entirely possible, and in fact it is the case, that people who are naturally more impulsive are more likely to use drugs and are more likely to transition from casual use to a problematic pattern of use. However, methamphetamine exposure can also induce impulsive choice behavior in animals without pre-existing differences in impulsivity. So this is what I alluded to before. And this was first shown in 1999 in an experiment that allowed rats to make a choice between a small amount of water, they were thirsty rats, a small amount of water delivered immediately, and a slightly larger amount of water delivered a little bit later. And what this allowed them to do is that when they chose between the two options, when they chose one option, then the other one would change the amount of water a little bit. So what we got is the point at which these animals were indifferent, that indifference point that I talked about with delayed discounting, were indifferent between the two reward sources. As you can see, in the animals that were treated with methamphetamine, in the absence of pre-existing differences, they valued the later reward less than the animals who were treated with saline. So this suggests that drugs of abuse, including methamphetamine, can induce impulsivity, but can it change D2? The answer to that is yes, indeed, it can. Methamphetamine, in the absence of pre-existing differences, can cause reductions in striatal D2 expression in animals. One thing that I want to point out here, though, is that this assessment, where we saw this difference, occurred 2 weeks after the animal had stopped being exposed to the drug. And then this follow-up assessment occurred 7 weeks after the animal had stopped using the drug, stopped being given the drug. So one thing that we can't really tease out of this is it the drug itself that's causing the reduction in D2, or maybe it's withdrawal that's causing a reduction in D2? With that in mind, I did an experiment to look at the time profile of D2 reductions in these animals. So what I did is I treated animals with methamphetamine for 2 weeks, an escalating regimen, which is thought to model human use. And then I tested how much D2 they had and how much of the precursor mRNA, or Drd2, they had that eventually gets turned into D2. So what I found was that immediately after they had received their last dose, in reality it was about 18 hours, but it was a short period of time, indeed we saw a reduction in the mRNA that coded for the D2. This actually got worse when I assessed them 6 weeks after they had last received the drug. So the withdrawal actually made this worse. This isn't altogether that surprising. What I found very surprising is that when I actually assessed the D2 expression, I found a significant increase in D2 expression 18 hours after the animal's last exposure to the methamphetamine. And then I found a decrease in D2 expression 6 weeks afterward. This suggests that it's actually not the drug that's causing a reduction in D2. It's probably more the withdrawal, or the experience of withdrawal. So with that in mind, let's kind of think about what this withdrawal is. One thing that I do want to point out is that if it is withdrawal and not the drug, a characteristic of the drug itself that induces these changes in D2, this shouldn't be specific to methamphetamine. Any drug which elicits a robust withdrawal syndrome should induce the same behavioral and neural effects. In fact, it turns out that opioids, cocaine, nicotine, and alcohol, all of which have severe withdrawal syndromes, all induce steep delayed discounting, and all induce decreases in D2. The converse hypothesis to that is that any drug without a severe withdrawal syndrome, such as marijuana, should not induce similar behavioral or neural effects. And indeed, marijuana users do not discount delayed rewards more steeply than controls, and they do not have decreased D2 expression relative to controls. So this withdrawal seems to be a really important part of the drug cycle in the development of impulsivity and in D2 changes. So let's look at withdrawal. Withdrawal is, I'm moving back to just talking about methamphetamine now. Withdrawal from methamphetamine is characterized by lethargy, stress, dysphoria, anhedonia. It's a very unpleasant experience. Nobody likes it. And it lasts about 7 to 10 days. And when we assess the sort of severity of it, we can assess this with a questionnaire, and we can see that these amphetamine withdrawal symptoms are elevated for about 7 days, and they slowly decline relative to healthy controls. However, they never quite reach the same level. These amphetamine withdrawal symptoms never quite reach the same level as healthy controls. They always stay somewhat elevated. So this time frame is what we're going to call protracted withdrawal. And it turns out that the symptoms that stay elevated are increased sleep, increased appetite, carbohydrate craving, and hyperphagia, meaning eating a lot. This, we have no idea how long it lasts. No study that has assessed this has ever seen a decline or a decrease in the protracted withdrawal phase. This relationship between withdrawal and eating a lot made me curious about the relationship between D2 and eating a lot. And it turns out that during protracted withdrawal from methamphetamine, people with low D2 expression had high caloric intake. So people who didn't have a lot of D2 were eating a lot. This made me think, could this possibly be an adaptive mechanism that the brain has evolved to increase food intake when the brain detects that resources are scarce? Now that's a jump, so I'm gonna justify that. But there is some evidence to suggest this. So rats that have been raised with scarce resources show increased impulsive choice behavior in adulthood. Rats that are raised in an impoverished environment, they also show decreased D2 expression. So being raised in this sort of resource-poor, impoverished environment causes decreased D2 expression and impulsive behavior. It's possible, therefore, that impulsivity is resulting from an increased sensitivity to the opportunity cost of exploiting the preferred option. And what I mean by that is that when you are waiting to get a later reward, you are missing out on opportunities that are coming by, and you're passing those by. And when you don't have a lot of resources, then maybe it makes more sense to get what you can get when it's available and not wait for the promise of something that might be better, that might be coming. In the wild, any time or energy that is used to exploit a difficult or a delayed reward source must be recovered through increased foraging behavior later. Therefore, when rewards or resources are scarce, it is adaptive to discount the value of hard-to-get or delayed rewards in favor of a smaller but more immediate alternative. In other words, when there aren't a lot of birds around, a bird in the hand is worth two in the bush. So that might be a relationship between impulsive behavior and substance use disorder, and it all has to do with withdrawal. But why do we care? We're all here to treat patients and to improve how we treat patients. So what does any of this have to do with patient care? How can we use this knowledge to protect patients from impulsive behavior during protracted withdrawal? So if this whole hypothesis about withdrawal is correct, an animal that experiences methamphetamine but does not experience withdrawal should not be impulsive. So I'll get to that in a moment. In order to assess this, I didn't look at delay, I looked at effort. So first I need to convince you that delay and effort are interchangeable. Effort, or how difficult a reward is to get, independent of how long it takes to get, can cause a reduction in the value of the reward in much the same way. So here is showing a graph with delay, and here is showing a graph with effort. The discounting functions look exactly the same. And additionally, people who are more impulsive show steeper discounting both of delay, of reward value by both delay and by effort. And they look very similar. So I put together this task looking at effort discounting. I used what's called a progressive ratio, in which the rat was able to press a lever and get a sugar pellet, but then the next time it wanted a sugar pellet, it would have to press twice. And then the next time after that, it would have to press 4 times, and then 6 times, and then 9 times. It gets more and more difficult to get the reward as the rat gets more rewards. And so what we can do with this is we can assess a break point. We can assess a point when the rat says it's not worth it anymore. Now, just to make things interesting and turn this into an actual test of effort discounting, I introduced another option. I put a ramekin full of normal lab chow into the cage with the rat. So now at this point, the rat is making a choice. It's choosing, do I work for this better reward that I really want, this sugar pellet, or do I just go eat this free reward? And when we look at the breakpoint there, we can really assess discounting. Going back to just sort of our theoretical model so that I can really make us understand this a little bit better, here we can see the value of the sugar pellets, the value of the chow in blue, and I'm going to show you what happens when a theoretical shallow discounter does this task and a theoretical steep discounter. So they both start pressing at about similar rates, and then eventually the steep discounter is going to reach its indifference point sooner or at a lower effort requirement than the shallow discounter. So if methamphetamine-treated rats are more impulsive in this effort model, they should stop pressing the lever sooner or at a lower effort requirement than the saline-treated rats. And there should be no effect on their chow intake. And indeed, that's what I saw. So when I tested rats in this test, I found that the methamphetamine-treated rats gave up earlier and switched to the chow. So this suggests that they are indeed more impulsive, not entirely a surprising finding. So the question is, can we do this test in rats that have been exposed to methamphetamine but have not gone through withdrawal? And the short answer to that is no, we cannot do that, because this task takes about 3 weeks to train the rats on, and that's after you've treated them, and withdrawal lasts in a rat for about 5 days. So no, you can't do it. But we can do kind of the next best thing, which is we can make withdrawal easier for the rat. And I did this pharmacologically. So many of the aversive and depression-like symptoms of withdrawal are mediated by a molecule called the kappa opioid receptor. And it's been shown that if you block this, then the animals don't feel the aversiveness of withdrawal. So I treated animals with methamphetamine, and then on the very first day of withdrawal, I gave them a blocker for this kappa opioid receptor. So the rats who received this blocker should theoretically, if my hypothesis is correct, the rats who received this blocker should be about the same as the rats who never received any methamphetamine at all. And indeed, that's what I found. So here are the rats who only ever received saline. Here are the rats who received methamphetamine and went through withdrawal with all of its aversive symptoms and nature. Here are the rats who received methamphetamine and did not go through withdrawal. They received this compound which blocked the aversive effects of withdrawal. And as you can see, they are approximately even. So one thing that did happen is the rats who were treated with saline and then given this molecule to block the effects of withdrawal from saline, they actually ended up eating a lot more of the chow. It just made them hungrier, which I don't have an explanation for, but maybe don't take this withdrawal drug if you're not going through withdrawal, just in case. So it really does look like the aversive and depression-like symptoms of withdrawal are necessary for the impulsive-like behavior in protracted withdrawal. So in conclusion, it looks like this model that I proposed has support, impulsive behavior can result from reduced D2 expression, which can cause inhibitory signals coming from dopamine reductions to be missed. Additionally, the aversive depression-like symptoms present during acute withdrawal may be able to decrease striatal D2 expression, leading to impulsive choice behavior. And alleviating this aversive state of acute withdrawal can help to restore inhibitory control during protracted withdrawal. This has some important implications for treatment. So for the past 50, 60 years, the front line of the United States war on drugs has been incarceration and mandatory minimums. If you are forcing someone to go through withdrawal and to detox during this incarceration period, you are making a bad time even worse. This probably makes the effects on impulsive choice behavior later in life, once they've moved on, even worse. Efforts should be made whenever possible, according to this hypothesis, to ease the withdrawal process, either through assisted detox, nutritionally assisted detox, making life easier if there are drugs such as methadone or buprenorphine, which can ease the withdrawal process, make it less sudden and bad, then that should be used if possible. Additionally, when there isn't a drug like that, contingency management is a very strong candidate for future research into relapse prevention. Contingency management is a relapse prevention strategy where you essentially pay a recovering addict for a week's worth of clean urine. So you go for a week, and if they test clean, you give them $10. The next week, if it tests clean, you give them $11, and so on and so forth. And if it tests with the drug, if they've relapsed, that's fine. You don't punish them. You just don't give them that money, and then you maybe reduce the amount back to 10. So you increase for the consecutive weeks. This is really good because not only does it take advantage of the fact that these people are naturally more impulsive, and therefore they want more regularly spaced, sooner rewards rather than the long, far off, difficult to acquire reward of sobriety. It's a little easier if you give them something short-term to work for, but also it's easing this withdrawal process. It's providing these regularly spaced rewards to the person that may ease the impact of withdrawal. So with that, I'd like to acknowledge all the people who helped me with this work, my lab at UCLA, my committee, Dr. Gomez-Pinilla, who helped with some of the biochemical work, and all of my funding sources. Thank you.